G'day Year 12s. So what we'll do today is get knee deep in the discrete random variable. So what we've looked at in the last lesson was sort of a review of Year 10 slash Year 11 probability. We really get into the Year 12 type stuff today. So a random variable is a function. So again, that's interesting because what we're linking probability with is our function-based maths that we've been doing since the start of the year. And what we do is we assign a number to each outcome in the sample space. So a random variable x is said to be discrete if it can assign only countable number values. And these numbers don't necessarily have to be whole numbers. So people talk about discrete numbers or discrete variables and say that it has to be a whole number. It doesn't have to be. So another example, an example of that would be shoe size. Like I actually take a 9.5 shoe size and I'm really fussy. Like it's got to be 9.5. If someone said, oh, we've only got nines, I will not buy them. It is a 9.5. But that is a discrete shoe size because it's 9.5 or 10 or 10.5 or 11. Okay. The number of tails when obtained when four coins are tossed together. That would be a whole number because you can either get zero tails, one tail, two tails. So that would be one that would be a whole number value. Now we can have a continuous random variable. So this is going to be discrete random variables. This is what the focus is at the moment. We can get a continuous random variable as well in probability. And examples of that are heights, ages, weight. All of these things are found by using some tool to measure the amount. Right, but we'll do that in about 2 to 3 weeks, I think. So a probability distribution that consists of all the values of x that a random variable x can take, together with the probabilities of each of those values, p of x, or the probability that the random variable can be this value here. So these two are the same. P of x is simply the function way to express this. P of x equals the probability that the random variable can take on this particular value. That would be seen to be interchangeable. You can write both of those. Okay, so here's our first example. Consider rolling an ordinary, fair, unbiased, six-sided die exactly 3 times in a row. So suppose the variable of interest is the number of fives rolled. Okay, so we usually do this. Let x equal the number of fives rolled. So if x represents the number of fives rolled, so again, you should do this formally, even though this kind of says this line here, then the probability distribution for x is, well, what are the possible values the random variable can take on? Well, we can get, if we roll the dice 3 times, we can get no fives, we could get 1 5, we could get 2 5s, or all of them could be fives. What are the chances of that? Well, we'll find out in a sec. All right, so what I'll do is I'll do the this. It's asking for the probabilities to 4dp, and I kind of wondered why, because we can get the exact value of these probabilities, but I can see here that the notes have us plotting this distribution, so I can see kind of like why it's important to have a dp approximation. So let's get 0 5s. So the way this is going to work is when I roll the dice, I either get a 5 or I don't get a 5. The chance of getting a 5 is 1 in 6, or not 5 is 5 in 6. Now I know this because this is a fair dice. All right, and what I'm going to do, I'm rolling it 3 times. So it's 5 or not 5, 5 or not 5, 5 or not 5. You're probably watching me in double speed at this moment, so I'll stop talking and do this. Okay, so this is going to be 1 in 6, 5 in 6, because the events are independent. Okay, almost there. Now, you'll recall maybe from year 11, and maybe you won't, but this is actually a binomial experiment, but more on that later. So what we're going to get is, let's get 3 5s first of all. So it's a 5 followed by a 5 followed by a 5. So that's going to be 1/6 times 1/6 times 1/6. So that's going to be 1 over 6 to the 3. What's 6 to the 3? 6 times 6 is 36. 216, I think. So let's just get the approximation for that. 1 over 6 to the 3. And I want to force a decimal approximation. So it is 0.0004. What do we want? 4 dp? 4, 6. All right. So a very low chance of observing 3 5s in a row. Like if you rolled that and said, wow, what's the chances of that happening? Let's multiply that by 100 and I'll tell you what the chance is. There is a 0.5 chance, so a 0.5% chance of rolling um, 3 5s in a row. So very slim probability. All right, let's do 0. So 0 5s, there's going to be a much higher chance of that because that's not 5, not 5, not 5. So that's going to be 5 to the 3, which is 1, 2, 5, over, I think 6 to the 3 is 216. I better check that. Yeah, it is. 125 over 216. And we can see that to 4 decimal places is going to be 0.5787. Okay, now 1 5. So that would be 5, not 5, and not 5. Not 5, 5, and not 5. Or finally, not 5, not 5. Ooh, am I going to get one? Yes, I got one. All right, so they're the 3 possible ways that I can get um, only 1 5. So I can get it first, I can get it second, or I can get that 1 5 third. Okay, so the way we're going to do this is, because the probabilities are the same on each of the branches, all I'm going to do is just work out one of them and multiply it by 3. Now you might remember from last year you can use binomial PDF on this, but more on that later. If you don't know what I'm talking about, that is fine. 1/6 times not 5 was 5/6, of course, times 5/6, and we're going to multiply this by 3. All right. So let's grab the approximation. So it's going to be, see, 1 over 6 times 5 over 6 times, it's a bit of a pain to do fractions on the calc, 5 over 6, and times that by 3 because there's 3 branches in total. So that's 25 over 72. Let's get that approximated. 0.3472. Okay, so now we're going to get this last one. I could do 2 successes or 2 5s, but what I'm going to do is just use a rule for probability, which is that if I add together all of the probabilities that I've got, which is uh, this one, and this last one I got, and then I go one, take away that, what's left over will be this one here. So that's 0.0694. Okay, so we've got our probability distribution function here. So again, this could be P of x equals P of x. So P of 0 produces this, P of 1 produces this, P of 2 produces this, and P of 3 produces this. This is why we call this a probability distribution function, because the probability is a function of the x values, okay? What would P of 2.5 be? Undefined. There is no 2.5 in this probability distribution function. Anyway, I'm getting off track. All right, so let's put in our values down below here. So we're going to go 0 at the origin, then 1, then 2, then 3. All right, so this is going to be split basically. So the highest value is going to be 1. So let's put 0 0.1, 0 0.2, 0 0.3, 0 0.4, 5, 6, 7, 8, 9, 10. Okay, so that's 0 0.1, 0 0.2, 0 0.3, and 1. All right, we really didn't need to go that high actually because really the highest probability is 0 0.6, but anyway, it doesn't matter. All right, so 0 was 0 0.578. So let's roughly kind of do that. That's roughly a little bit lower than 0 0.6. Put that there. Okay, 1 was 0 0.34, so around about halfway between. So there. This one was 0.07, so a little bit over halfway. So here would be halfway. Here's that one. And 0.04 is really low. Okay, so that is somewhere down here. Okay, so these are our values. Here you can mark them as individual points if you want. 0, 0 0.5787. You don't have to do this. 1, 0 0.3472, etc., etc. Now, what we are not going to do here is join the dots. So we don't draw a curve over the top of these because this is discrete data. Okay, so it's very important. Do not join dots. Okay, because if you do, then there's a line there, and that means that 2.5 will produce a value because you've got a line joining it. Okay, so the only time we want to produce values is if 0 is inserted into the function, 1 or 2 or 3 is inserted into the function. Anywhere else, basically the function is not defined. All right, so the random variable y represents the number of sultanas in a certain brand of biscuit and is known to have the following following probability distribution. I'm making up words. Okay, so you're either going to get 4 sultanas, 5 sultanas, 6 sultanas, or 7 sultanas. And the chance of getting 4 sultanas is basically there's a 5% chance, 30% chance, 45% chance. Ooh, I wonder what this is. Well, again, if this is a probability distribution function, then this value here is simply going to be 1, take away all of this stuff here. So let's quickly do that in our head. That's going to be 5, 8, so P is going to be 0.2. Probably need some calculations on that. So we're going to say that 0.05 plus 0.3 plus 0.45 plus P has to equal 1. Therefore, P is 0.2. Okay, find the probability that a randomly chosen biscuit contains at least 6 sultanas. So we're looking at the probability that the random variable contains at least 6 sultanas. So that's the probability that the random variable is equal to 6 plus the probability that the random variable is equal to 7. Okay, so 0.45 plus 0. What was it? 2 is 0.65. Okay, find the probability that the random variable is between 4 and 6. So that is going to be the probability that it's equal to 4. Well, I keep stuffing this up. But the random variable is equal to 4 plus the random variable is equal to 5 plus the random variable is equal to 6. So 4, 5, and 6, that's these three here. So that was 0.8, I think. Okay, so here is our conditional question, and this is the way they invariably go. So the chance that it's greater than or equal to 5, given that it is less than or equal to 6. Okay. So what we know is that the sample space now is not 1 anymore because this can't happen. We've been told that the random variable is less than or equal to 6. So it's given that this condition here, okay? So let's rewrite our statement here. So we've got our numerator on our denominator. It's not over 1 anymore. It's over the smaller sample space. It's going to equal to 6. Okay, and what we want is the chance that the random variable is larger than or equal to 5. So that's going to be 5, 6, or 7. But because we know already that 7 can't happen, it's going to be either 5 or 6. Okay, so we've got the probability that the random variable is equal to 5 plus the probability that the random variable is equal to 6. Okay, so they always test this, like, because what a lot of students do with this problem here is they just write probability that y greater than or equal to 5 over the probability that the random variable is less than 6. And then they just get y greater than 5 or greater than equal to 5. So they do all of these. So you just got to think about what this condition has in terms of its ramifications on this one here. Okay, so it's equal to 5 plus 6. So 5 and 6 was 0.75 over less than 6. What was that? 0.8, I think. Yeah. Which is 75 on 80, which is 117 on. Oof, how many times does 5 go into 80? Struggling here. 1, 3, 6. That's not a good outcome. Let's just try that again. 1, 3, 7. Okay, this is going well. That should be a 2. That's 15. Now, again, important that I'd love to say I'm doing this on purpose, but I'm not. But the fact that the numerator is higher than the denominator for a probability is a really, really bad sign. Okay, so the answer couldn't have been 17 over 16. So there's our answer there, 15 on 16. Now we can't leave our probabilities as a decimal over a fraction, so it has to be converted one way or the other. So you either have to go full decimal or full fraction. In this case here, this is just a standard tech-free problem. So using fractions is going to be the easiest way to do that problem.